Hi, welcome to the Sedra Smith MOSFET small signal analysis. In this video, I'm going to show how to derive or calculate the gain. I'm going to start off with the common source configuration, just in case don't know how to differentiate between common source, common drain, and so forth topology. What you have to know is if your signal is coming in, here's your signal, and if it comes in, the signal goes through the cap and it's going through the gate. There's the gate, here's the source, and here's the drain, and here I have the out. So basically, if the signal goes into the gate and then it comes out to the drain, okay, so basically you have your input going to the gate, output coming to the drain. So what do you have common that is both common to the input and the output? Your source is common to both. So that's why it's called a common source. Okay. So just want to get that out of the way. Make sure that that's why it's called that, because it's common to both the input and the output. Okay. And basically common drain, common gate, it's the same thing. Basically you see where the signal goes in, where the signal comes out, and the node or the terminal that is common to both, then you call it common whatever, either common gate, drain, and source. Anyway, so to derive the voltage gain, you have to use a small signal model, which you should be already familiar, and I'm using the simplified one. So this is going to be the gate, that's the source, and this is the drain, and then this current source flows like that, and you can call it ID if you wish, and it's GM, which is the transconductance, times VGS. Now the VGS means it's the voltage that is applied from the gate to the source, with the plus being up here on the gate and the negative being the source. So what you do is you use this model and insert it into the circuit, and when you do an AC analysis, what you want to do is any voltage sources, you set them to 0, and because they're at 0, you can assume that they're ground. Okay, so in this case you have a let's say this source is 0, so basically it's a ground. Okay, now when I say voltage source, you want to keep this is going to be your VN. Okay, and second, assume that the capacitors are big, meaning large capacitance. Okay, and you treat them as if they're short. So in this case, you see a cap, short, and you short across it. Okay, so now the third is insert your small signal model, SSM. Okay, and I'm going to zoom out a little bit so you can see the schematic. Okay, so we're going to redraw it. And here's V. And what I'm going to do is I'm going to change it from VN to VS. Hang on. Let me go ahead and I'll keep it as VN. I don't want to get you confused with the VS being the voltage across the source. Okay, so then we put RG here. Okay, and then since this point is ground and this point is ground, or you can assume it's ground, they're connected together, and if you see that this is in parallel with that to ground, so you can draw a resistor and you say R1 in parallel with R2. Okay, so then this is where you insert your model. This is your gate, and this would be your source, and then this is connected to ground with your source. GM times VGS, and then you go through the capacitor. Capacitor is shorted. You do have an RD. The RD is connected to ground, and your load is connected to ground. So you can actually put these as one resistor and just say that RD is in parallel with RL, with your R load. Okay, so now you have the small signal model set up. Okay. So now let's see, what do? So first you try to define your VGS. Okay. And a technique or a simplification that I like to do is that VGS, when you're talking about VGS, you're actually taking a differential across two nodes. So you can write VGS as VG minus VS. Okay, so I like to use this equation a lot because it simplifies stuff. Okay, so what I want to do is derive an equation and express VG, which is that VG. Okay, and just by inspection we can see that VG is equal, okay, VN times the parallel combination of R1 plus R2. You gotta realize that you're forming a voltage divider, right? Okay, so it's a summation of both. So RG plus R1 R2. Okay, so now we're ready for VS. If you notice, VS is connected to 0, so that goes to 0. Okay, so now we can say that VGS is equal to, let's see if I can do this. Copy. Let's do that. is equal to that. Okay. Alrighty. So now we need to find an expression for V out. Okay. Now if you notice here, this is the current source, and this current source is a dependent, and it's dependent on whatever the voltage is that you see between here and here. Okay. So as it flows in this direction, okay, it goes to ground. That means that it has to return, and it returns in this direction. Okay. So it's flowing up. Now if it's flowing up, that means that this is positive and this is negative. So you're going to have a negative voltage. Okay. So the negative means that it's inverting. Okay. So in other words, you're going to have a 180 degree shift. Okay. So keep that in mind. So now we can kind of start writing an equation, and we can say that, and we can think of this as ID, current through the drain. So we can say it's negative because we know that it's going up, and we can say it's ID times RD divided by RL. Okay. So now ID, or the gain, or the current of the drain, is really GM times VGS. We substitute that in there. GM VGS. And now we substitute all of that into VGS. Okay, and let me backtrack a little bit. Okay, forgot to carry this over. Okay, so it's RD with RL extended, and then bring the VN to this side. So there you have it. So the gain is supposed to be negative GM R1 R2 times RD with RL RG R1 parallel with R2. So that's the derivation of a common source. Okay, so that's that. Let's go ahead and do another one.